So it's becoming a tradition to chase down grading and scoring and organizing and sorting all the tests by doing the bonus problem on YouTube. I like that a bunch of people got to do the bonus problem today and had a lot of interest in it, and that there were a lot of really strong attempts. Obviously not everyone got it, but there were some strong attempts made. I think there were 6 or 7 people total who got the full points, and I think 3 or 4 others who got a couple points for getting to a key step. Now, there were multiple approaches you could have taken to this bonus problem, which is focused on integral functions as well as just some other basic geometry. One of the approaches, which is the one that Mr. Nickerson took with it when he looked at the problem, was to purely use geometry and then sort of kind of shift things around afterwards. That's not the approach I'm going to use just because this is a Calculus AB class, so I'm going to try to approach it as much like Calculus AB as possible, but know that it is geometrically possible, and at least one of the people who solved it correctly in my class did it that way. On the other hand, though, I don't claim that this is the most efficient process in the world, but it is a process that works, which is the important part here. So I have, I believe, the 6th period version of the bonus question, simply because I did 2nd period last time. So I'm going to work through it and do the problem. So here we go. So in this situation, we have a continuous function f of x. That's what's graphed over here. And I will admit that I probably should have labeled it and said, like, hey, here's f of x. We'll do that right now. So this is f of x. And it has 2 semicircles and a line segment. So cool. So it's defined for -8 to 14, it looks like. It then wants us to define the integral function b of x, which runs from -8 to x, which is pretty standard. It starts at the left endpoint and accumulates area as it moves to the right. There are 2 zeros on -8 to 14. One is at x equals -8, which makes sense because that would make our integral run from -8 to -8, so that is definitely a 0. The other is at x equals c. They want us to find the value of c. So the idea here is that somewhere along this line is some value x equals c that would make this integral function, or in this case b of x, equal 0. So how are we going to approach that? Well, here's the general idea. And I'm going to use the word cancel, even though the word cancel isn't mathematically rigorous. I just think it kind of gets the idea across much faster. Basically, we want the negative area on the left side to cancel out the positive area on the right side. So think about that idea. We want the negative area and the positive area to cancel each other out. That means they need to have the same magnitude. So the way I'm going to start this approach is I'm going to point out that on the left side we have a semicircle. The semicircle has a radius of 4, and that means that the area on the left side is going to be 1/2 pi times 4 squared. So I'm starting there with just letting it be positive because of the fact that we want the two areas to be the same. That would mean they would cancel because the one on the left is below the x-axis, the one on the right is above. So there's our first bit. Java update. No. The second thing I want to look at is now on the positive right side. Well, what do we have over there? Well, on the right side, we do have this little mini semicircle, but I can tell that's not going to cancel out the area of the much bigger semicircle on the other side. So I'm just going to point out that first we have 1/2 pi times that radius squared. And that is, of course, going to be part of it. And since this one has it looks like a radius of 2, since the diameter is 4, we'll put that in there. And then second, this is where it's going to get kind of interesting. Second, we've got the portion that comes with this little triangle here. So that little triangle piece is going to be represented by an integral. It's going to be the integral from 4 to c, because c will be the place we stop. That gives us 0, because the two areas will cancel each other out. And then it'll be of some function dx. The function on the inside is going to be this line. So we need to figure out what that line's equation is. Fortunately for us, that's going to be pretty easy to calculate. First of all, our line is going to go through the point 4, 0, which means it'll be of the form y equals m times x minus 4 plus 0. So we don't even really need the plus 0. Let's dump it. Second, we need to find the slope, but we can calculate the slope with just sort of a classic slope calculation. We'd have these two pieces be like so. That would give us a slope of 20 minus 0 over 14 minus 4, which is, of course, 20 over 10, codename 2. So the equation we're looking for, or the equation we're going under, is 2 times x minus 4. Now that means our integrand is going to be 2 times the quantity x minus 4 as well. Now when I did this earlier, I distributed it out, but actually a student in my 2nd period class on their separation of variables problem did a really cool thing with a similar integral. So I'm going to actually do the exact same thing. This integral is going to be the integral, or is going to antidifferentiate to x minus 4 squared. And I'll let you think about that. If not, like you can work on that on your own. I'm just going to present it as knowledge. Again, that person had a really cool solution, so I want to honor it. On these other portions, we have half of 4 pi, which is 2 pi. And on the other side, we have half of 16 pi, which is 8 pi. And of course, this whole thing is equal. Well, I'm going to move the 2 pi over, just kind of clean this whole thing up. That's going to give me now on this side 6 pi equal to that right side, the result of the fundamental theorem. Well, the fundamental theorem result will be c minus 4 squared minus 4 minus 4 squared. Well, that last bit is just 0, so really we have to solve the equation 6 pi equals the quantity c minus 4 squared. And again, c is going to be our 0. It's going to be the value that makes the two areas cancel out. Or it makes the magnitudes of the two areas the same, which is the same thing as, undoing one another or zeroing each other out. So from here, I want to solve this equation. So, okay, I can do that. Let's go right at it. I'm going to square root both sides. Of course, when we square root that, we get an absolute value. I'm going to play it simple. We'll get plus or minus the square root of 6 pi equals c minus 4. And of course, you can add 4 to both sides, and you too will see that c is going to be 4 plus or minus the square root of 6 pi. Now, no one stopped here, so I didn't have to make a decision on scoring an answer like this, but this isn't the correct answer, and it's pretty obvious why. For one, the problem said there's only one more 0, so it can't be both of them. One has to be incorrect. Second, just from looking at our picture and thinking about the size of those semicircles, we should be able to tell that our value of c has to be greater than 4. We need some of the area from that triangle in order to accumulate enough to counterbalance or counteract the negative area on the left side. So in other words, if c needs to be greater than 4, it has to be true that c is equal to 4 plus the square root of 6 pi. Now, I don't have a calculator handy to give you the decimal value. I think it ended in 342. It might have been 8.342. Just checked, it was indeed 8.342, so that would have been an acceptable answer as well. I think a couple of you wrote that, in fact. But in any event, there is the solution to the bonus problem. As I said, I'm not going to do the geometric one, but obviously it accomplishes the exact same thing, just through a different path, which sort of avoids the integral. But like I said, I wanted to do the Calculus AB version because this was for a bonus question for a Calculus AB test. In any event, I'm going to stop right there. I am freezing. I haven't eaten. And I have a headache from grading, what would it have been, like 68 tests, I think, today? No, 76 calculus tests. 74 calculus tests. So I'm going to call it a day. So hopefully that was illuminating. Thanks to everyone who attempted the bonus question, and for everyone especially who asked about it and wanted to see this. Hopefully this illuminates your approach. And again, this was 6 periods version. Second period, I want to say, was like 8 plus the square root of 10 pi or something like that. So again, each one had a slightly different variation on it. But there it is. Thanks for watching. Have a good night.